Good morning, champs. Why does gas heat up during compression, and why does the temperature rise depend on the process path? In the last video, we saw that different compression paths require different amounts of work. Now we quantify how strongly the gas heats up. We start with the ideal gas law. This tells us that pressure, volume, and temperature are directly connected. Now we combine this with the polytropic relation. A polytropic process follows P times V to the power n equals constant. This equation describes the compression path. Now let's derive the temperature relation. From the ideal gas law, temperature equals P times V divided by mR. For a polytropic process, pressure can be written as a constant divided by V to the power n. Now insert this into the ideal gas law. Temperature becomes constant times V to the power 1 minus n divided by mR. Since the constant mass and r do not change, temperature is proportional to V to the power 1 minus n. This gives the relation T2 over T1 equals V1 over V2 raised to the power n minus 1. So if the volume decreases during compression, the temperature rises. Now we can also write the relation using pressure. From P times V to the power n equals constant, volume is proportional to pressure to the power minus 1 over n. If we insert this into the temperature relation, we get T2 over T1 equals P2 over P1 raised to the power n minus 1 over n. This equation tells us exactly how strongly the temperature rises during compression. Now let's interpret the exponent. If n is small, more heat leaves the system, so the temperature rise is smaller. If n is larger, less heat leaves the system, so the temperature rise is stronger. For the isothermal case, n equals 1. Then n minus 1 over n becomes 0, so T2 over T1 equals 1. That means the temperature stays constant. For the isentropic case of an ideal gas, n equals kappa. This gives the strongest temperature rise among these idealized cases. Now let's calculate a small example. Air starts at 300 Kelvin. The pressure ratio is 5, so P2 over P1 equals 5. First, the isothermal case, n equals 1. The exponent becomes 0, so the temperature ratio is 1. Therefore, T2 equals 300 Kelvin. No temperature rise. Now the polytropic case. Use n equals 1.15. We calculate T2 equals 300 times 5 raised to the power 1.15 minus 1 divided by 1.15. This gives approximately 370 Kelvin, so the gas heats up moderately. Now the isentropic case. Use kappa equals 1.3. We calculate T2 equals 300 times 5 raised to the power 1.3 minus 1 divided by 1.3. This gives approximately 435 Kelvin, so this case gives the strongest heating. Now compare the results. The less heat leaves the gas during compression, the hotter the gas becomes, and the polytropic exponent tells us exactly how strong that temperature rise is.